You know, everything from the smartphone in your hand to a massive bolt of lightning, it all has to play by a very strict set of invisible rules. Today, we're going to pull back the curtain on the 3 unbreakable laws that every single electric charge in the universe has to obey. So what are these fundamental rules? What's the secret code that every charge follows, from a tiny electron to a massive power grid? Well, that's exactly what we're digging into. Think of it as the unwritten constitution for all of electricity. Okay, before we jump into rule number 1, we need to get one simple idea straight just to make things easier. We're going to imagine that for any charged object, all of its electricity is concentrated in one single tiny spot. We call this a point charge. It just helps us focus on the rules themselves without getting bogged down by complicated shapes. All right, so our first rule is, well, it's thankfully a pretty intuitive one. It's called additivity, and it's basically the simple idea that charges, they just add up. But here's where charge gets really interesting, especially when you compare it to something we all know, like mass. See, mass is always a positive thing, right? You can't have -5 kilograms. But charge, it comes in 2 flavors, positive and negative. And this is so important because it means they can actually cancel each other out. So how does that work in the real world? It's literally just simple math. If you want to find the total charge of a system of particles, you just add them all up. So you've got a +1, you add a +2. Then you've got a -3, a +4, and a -5. You do the math, and the grand total, a net charge of -1. It really is that straightforward. And that simple idea that charges add up leads us directly to our second rule. And this is one of the most powerful and fundamental laws in all of physics. It's the law of conservation of charge.
What this means is, for any isolated system, think of it like a closed box. The total amount of electric charge inside never changes. You can move it around, you can shift it from one object to another, but you can't create it out of thin air, and you can't destroy it. The grand total is always constant.
A perfect example of this is static electricity. You know, when you rub a balloon on your hair. You start with 2 neutral things, your hair and the balloon. The total charge is 0. When you rub them together, some negative electrons jump from your hair to the balloon. So now, the balloon is negative and your hair is positive. But what's the total charge of the whole system now? It's still 0. No charge was created, it was just rearranged. And this law holds true even at the mind-boggling subatomic level, where particles can literally pop into existence. For example, a neutral neutron can sometimes decay, turning into a positively charged proton and a negatively charged electron. The charge before this happened was 0. And after? Well, you've got a +1 and a -1, which adds up to 0. The law remains completely unbreakable. Okay, so that brings us to our third and final rule. And this one is probably the most bizarre of them all. It really messes with our everyday perception of how things should work. This is the principle of quantization. So what on earth does quantized mean? It means that electric charge isn't like a smooth, continuous flow of water from a tap. It's more like sand. It's made of tiny, individual, indivisible grains. You can have 1 grain of sand, or 2, or 1,000, but you can never ever have half a grain. Well, charge works exactly the same way. It only comes in these discrete little packets. This whole idea is wrapped up in a beautifully simple but incredibly profound formula. Q equals N times E. So Q is the total charge of any object you can find. E is that fundamental basic unit of charge, that one little grain of sand. And N is the real kicker here. It has to be a whole number. So any charge in the universe has to be 1e or 2e or -50e, but it can never be something like 1.5e. And just how small is one of these fundamental packets of charge? It is unbelievably tiny. The value of E is about 1.6 times 10 to the power of -19 coulombs, which is the standard unit for charge. That number is a decimal point followed by 18 zeros and then a 16. It's almost impossible to even imagine something that small. But hold on. If charge is really made of all these tiny, separate packets, that brings up a pretty big question. Why does electricity seem so smooth and continuous to us? Why does it feel like water and not like a pile of sand? Well, the answer is all about scale. At our big, macroscopic level, the world we live in, those individual packets of charge are just way too small for us to ever notice. It's kind of like looking at a dotted line from way across a room. It just looks like a solid, continuous line. It's only when you walk right up to it, or you zoom way in, that you finally see,
Oh, it's actually made of a bunch of separate individual dots. And charge is exactly like that. We're just experiencing it from too far away to see its true, grainy, quantized nature. To put a number on this that'll really blow your mind, a single Coulomb of charge, that's roughly the amount that flows through a light bulb in a second, contains about 6 quintillion of these basic charge units. That's a 6 followed by 18 zeros. When you have that many tiny little packets all moving together, it's really no wonder it feels perfectly smooth to us.
So there you have it, the 3 unseen rules of electricity. First, additivity. Charges just add up like simple numbers. Second, conservation. You can't create or destroy charge, only move it around. And third, quantization. Charge only exists in tiny, indivisible packets.
And that leaves us with a really fascinating final thought. The discovery that charge comes in these discrete packets was a total revolution in physics. It really makes you wonder, if something as fundamental as electricity is secretly built from these indivisible units, what else out there is? What other things in our universe that seem perfectly smooth are actually grainy once you get close enough? It's something to think about.